Welcome to MyProjectBazaar.com. Now we discuss about the product for high-speed and energy-efficient carry-skip adder operating under a wide range of supply voltage levels. Next we see the abstract for the product. Adder are a key building block in arithmetic and logical unit, and hence to increasing their speed and reducing their power and energy consumption strongly. This affect of the speed and power consumption of processors. There are the many works on the subject of optimizing the speed and the power of this unit, which have reported in obviously. It is highly desirable to achieve high speed at low power and energy consumption, which is the challenge from the design of general purpose processor. One of the effective technique to lower the power consumption of digital circuit is to reduce the supply voltage due to quadrative depending of the switching energy in the voltage. Moreover, the sub-threshold current, which is main leakage component of devices, and to exponential difference on the supply voltage level through the drain and inductor barrier lowering effect. Depending on the amount of supply voltage reduction, the operation of on devices may reside in the sub-threshold, near threshold, and the sub-threshold region. Working in the sub-threshold region provides with lower delay and higher switching and leakage power compared with the near and sub-threshold region. In the sub-threshold region, the logic gate delay and leakage power exhibits the exponential dependence on the supply and threshold voltage. Moreover, these voltages are potentially subject to the process of environmental variation in the nanoscale technologies. In this paper, a carry skip adder structure that has been higher speed yet lower energy consumption compared with conventional one. The speed enhancement is achieved to applying the concatenation and incrementation scheme to improve the efficiency of conventional carry skip adder logic. In addition, instead of utilizing the multiplexer logic, the proposed structure to make the under inverting and or and inverting component gate for the skip logic. The structure may be realized for both fixed stage size and variable stage size style, whereas in the latter for the improve the speed and the energy parameter of the adder. Finally, hybrid value of latency excitation of the proposed structure, which lowers the power consumption without considerable impacting the speed, is presented. This extension utilizes the modified parallel structure, reducing the proposed structure are accessed by comparing their speed and power energy parameter with those of the Addons technologies for a wide range of supply voltage. Finally, we design a parallel prefix adder with considerable smaller area and power consumption. Simulation on the proposed hybrid variable latency carry skip adder reveal reduction in the power consumption compared with the latest works in the field of while having the reasonably high speed. Next, we see the flow diagram for the product. Our product was developed in DSCH2 and MicroWin software. The DSCH2 software is used to design the gate-wise component or transistor-wise component in the platform. MicroWin to be converted into the DSCH2 design to convert the layout design and to calculate the power and timing energy level for overall adder architecture process. This adder architecture mainly doing the carry skip logic. We design a 32-bit input data bits based adder architecture, so we apply the half adder and full adder design for basic logical gate elements, and we develop the carry skip order logic using the 32-bit RCA ripple carry adder for logical gate addition and AOI gate addition and the carry selection process for logical function. Because we apply the even and odd mode section to add the AOI for the our carry selection and the skipping logic function. The incrementation logic, whenever the carry is set, the data bits to be incremented. If the carry is not set, the data bits directly presented to the our addition process. And to calculate the sum and carry function for the DSCH2 software, we represent these software and to update all the things. and we developed the 8-bit carry skip order logic design based adder design, and to convert the microevent to the layout form using the microevent software. The layout diagram to represents the how many logical structure to be presented in a layout manner and 3D form 3D manner in overall function for the carry skip logical architecture function. This is our the microevent based designs. We apply the 32-bit addition process in TH2 software. We apply the 8-bit carry skip addition for the microevent software. These two softwares to be combined, how to work with the carry skip logical function for overall addition process and reduce the power consumption and delay time for gate wise design and the layout wise design also. This is the overall flow diagram for the our addition architecture process. Next we see the final output for the product. First we open the DSCH2 part. The DSCH2 software to be run with run as administrator block. This software to be separate the platform and to select the file and open to the our final design. This is our final design for 32-bit based addition architecture. This is our the overall processing for addition architecture. This is our the each and every RCA block and the incrementation logical block, then AOI OI form based add or event based selection output. Then to starting simulation window, this simulate the overall architecture and show the pin status also. It represents the pin values and to apply the any one of the input and to represent the what are the output to be presented in our overall 32-bit addition architecture. This is our the final output architecture for the our overall process. Then to finalize the our graphical limitations also to be represent for the our DSCH2 software. This is our the output for our overall design. Then we go to the expand microevent part. This microevent to be represents the layout designs. This layout design to be opened for our required conversion logic and to examples SK for the our required layout design. This is our the 8-bit adder based layout architecture design. This is our the represent diagram for the gate logical layout design. This is our the clocking sources and to the addition architecture layout design. This is our the overall area for our layout architecture and to represents the running purpose for our layout based design. This is our the layout design based running purpose and to efficiently calculate the delay time and power consumption level for overall layout architecture. This layout to represents the 8-bit adder for using carry skip order logic. This is our the overall output and to calculate the power consumption for our 8-bit carry skip order logical timing and delay timing, all other things to be represented in microevent software. This is our the final output for the carry skip order logic based adder gate wise design and the layout wise designs, all the things also.